All right. Hello, students, and welcome to week 14. So, after tonight, just two more classes. So, we have next week's class, no class the following week because of Thanksgiving break, and then we conclude in that first week of December. And so, the last official day of the semester is going to be December 10th, and that will be when you want to have all of your CK12 work completed, as well as the discussion boards and such. So, let's get into this week. So, just as before, go to the home page here. If you go down to week 14 module, you're going to see the same four things you've seen the past few weeks. And so we have our discussion board. So I'm going to start there because it's a little bit different. So most of the videos that I found that deal with heat and energy transfer, which is what we're talking about this week, the videos were very long. They were very involved, and I didn't want to use those videos because I think it's hard enough to, watch a 3 or 4 minute one when you're not too familiar with the subject matter. So instead of that, I've just posed a question here to you that is answered within this lecture. So if you hold a hot cup of coffee in your palm gets hotter. If you hold an ice cube in your palm, the ice cube will melt. And so first off, we want to talk about what type of heat transfer is this, which we'll get to. But then also, why does your hand get hot while holding the coffee and the ice cube melts when you're holding the ice cube? It could be, you could be thinking it as simple as, well, the coffee's hot, so it makes your hand hot, and the ice cube's cold, so that's why it melts on your warm hand. But we want to be a little bit more detailed as we explain that, and we'll get to that later on. So that's your first part here. Let me hop back to the module. You have your CK12 link, as always, and if you click on that and you go to our classroom, you will now see week 14 heat. And if you click on that, so it's going to be 3 sections. So this week we're talking about thermal energy, temperature, and heat, and then there's your week 14 quiz. Now, the second section here on temperature, there is some math involved, and so what I've done with this lecture is I've included some worked out solutions at the very end of it, which we'll get to. But so just those 3 sections. So make sure when you go to them, so if you just click on this one right here for temperature, do the reading, watch the videos, look at the real world examples. The videos aren't very long, and so this one only has one. And a lot of the stuff that you'll be answering within the adaptive practice comes from some of these videos as well as the reading. So and notice here, this is a firm due date now, 12/10/2020. That is the very last day of the semester. And so that's when this would need to be done by. So now we have to have those, hard deadline dates because of, us wrapping up. So those 3 sections along with your week 14 quiz, and that's it. So let me hop back now to our module. And so, so this one here, the lecture and the PowerPoint is where you're going to find this that you're watching right now. And you will always have the PowerPoint available to you with no lecture, just for like study purposes, or if you want to go back over anything. So I'm going to start there. And so if you click on that, you're going to see the link out to the PowerPoint. And so let me hop to the PowerPoint now. Oops, didn't mean to hit that. There we go, present. All right. So we're talking about thermal energy and heat. And so we've had this pervasive and continual theme of energy. And we talked in the very, very beginning about how energy is neither created nor destroyed. It just gets transferred, whether it be to sound waves, to electromagnetic waves. We've seen many examples of how energy is transferred between substances, situations, and various waves on the electromagnetic spectrum. So our essential question for this week is, what is the relationship between heat and temperature? Some of the things that relate to heat and temperature, like something being relatively hot as opposed to something being cold. What is heat? What is temperature? How do we measure them? If you look on the back of any food label, you're going to see like how many calories it is. Calorie is actually a measure of heat in a substance. So we're going to explore all those relationships. Let's go ahead and start moving our way through it. So thermal. We're talking about thermal energy. So therm, obviously meaning heat, and now we're talking about energy due to heat. So thermal energy is simply the total kinetic energy of all the particles in a substance. If you recall from earlier lectures and sections, that kinetic energy is the energy of motion. So the more motion that we have, we're going to see a higher amount of thermal energy. So it is measured in joules. We're not going to get too much into the SI units for them, but it's good for us to know them. And if we just look at these two examples here, so if we had chocolate milk and then hot chocolate, if we take those two, obviously we're going to have a difference in temperature there. And so when substances are at a lower temperature, there's not much motion or kinetic energy between the particles or the atoms in the that make up the substance. Now, as we increase the temperature, or as we increase the amount of thermal energy, which we'll talk about the ways that we can do that, the particles are going to start to move around some more. They're going to have a higher kinetic energy. And because of that higher kinetic energy, they're going to have a higher thermal energy. So high temperature particles have a higher average kinetic energy, and the low temperature particles have a lower kinetic energy. So what is the difference between thermal energy and temperature? Because there's a huge difference. So temperature is related to the average kinetic energy of the particles. So if you took all the kinetic energy of all the particles, added them up, and took the average, there's your temperature. While thermal energy is the total kinetic energy of all the particles. Now, where this becomes very important is when it says all the particles, it gives us an idea that the size is very important, and we'll talk about that in a second. So, for example, a glass of water can have the same temperature as a lake. Say both of them are, relatively chilly at, 55 degrees. They can have the same temperature, but that lake has much more thermal energy because it contains way more water molecules than the glass of water. So the total kinetic energy of all the particles is what we have to take into account there. So that lake would have more thermal energy because of the fact that it is much larger and has more water molecules. So we're not just looking at the average, now we're looking at the total. So temperature and the total amount of particles determine the thermal energy of a substance. So even though they're at the same temperature, since there are more water molecules in the lake, it will have a higher total energy. So if we look at these examples here, if we want to talk about the relative thermal energy, so if we have a bowl of soup and a pot of soup, so if you just had a bowl of soup and it was at the same exact temperature as a pot of soup, well, you'd have to say that the pot of soup has more thermal energy because there's much more soup in that pot than there is in the bowl. Very much like the lake and the water glass scenario we were just talking about. Same thing with the small balloon and large balloon. Which one has more thermal energy? Well, that's just, they both have, air within them. And if they're at the same temperature, the larger balloon would have more air molecules in it. Therefore, we'd have to give it, the crown for thermal energy. So what has more thermal energy, a tiger or a house cat? Well, that's, assuming they're going to be the same temperature, one of them's not running a fever or anything, that tiger, which is going to be way larger than your average house cat, is going to have more thermal energy. So that gives us an idea of the relationship due to size, even though things may be the exact same temperature. So when we talk about heat, it's like a lot of things in this class, it's something we talk about all the time. We're very familiar with the term, but in terms of what it actually is and what it represents, you'll be surprised at how involved it gets. So heat is just the energy transferred from an object at a higher temperature to an object at a lower temperature. Now, this is very important because this is a rule of thermodynamics that says heat can only transfer from a hotter body to a cooler body. Not just, human body, but just any object is referred to as a body. But so when we're talking about the discussion board of why does your palm get warm when you're holding a hot cup of coffee, but when you're holding an ice cube, it melts? Well, now if we think about it in terms of relative heat, if you have that mug of coffee in your hand, it is much hotter than your hand is. And so the heat transfer is going to go from the mug to your hand. To where if you're holding an ice cube, well, now your hand is much warmer than the ice cube. So that flow of heat is going to go from your palm to the ice cube, which is why it melts. So once again, the whole heat can only transfer from a warmer body to a colder body. That's the only way that it can happen. And so technically, if you want to be really annoying, if anybody ever says like, oh, I'm getting colder, You can say, no, you're not. You're just not as warm, because that's the direction heat will flow. Now, don't be that person. I've been that person many times, and you don't get good results from it. So energy in the form of heat always flows from hot to cold. That is just how it's going to go. So if how like sometimes people can have like really cold hands if they put their hands on you, like it's really cold. Um, all that's happening there is the heat is being transferred from your warm body to their cold hands. And so that's the way that the energy is always going to flow. It's never that someone is making you colder. They're just sort of stealing your heat, if you will. All right. So we're obviously not in class, so we don't have to worry about drawing arrows in the direction. But if we're just talking about how heat would flow, knowing what we know now, so if we had a metal rod and we put a flame to it, the flame is going to be much hotter than the rod is initially, and so that direction of heat would be flowing from the fire into the rod. Now this next one seems weird: a hat and a snowman. Well, one thing that a hat is going to do, it's going to hold in the heat from your head. Now, obviously, the snowman isn't alive unless there's been some weird, frosty style spell put on it, and that's a whole different nightmare we don't want to get into. But that hat is going to hold in any, air molecules that would otherwise escape, and therefore it'll hold in heat. And so, in that case, the hat is going to be where the heat is flowing from the hat to the snowman. And then if we look at an ice cube and a warm glass of water, well, the warm glass of water is going to melt the ice cube. So therefore, your heat is flowing from the water into the ice cube to make it warmer and melt it. As opposed to saying, oh, well, the ice cubes are cooling down the warm water. No. I mean, sure. You can think that way, absolutely. But in terms of what is scientifically correct, it is the heat going from the warm water into the ice cube. So energy as heat is flowing from the warm bodies to the cold air. There you go. So how is heat measured? It's measured in two ways. And one way is the calorie. So 1 calorie, the technical definition, because, we could say something is, 3 grams, and it kind of gives you an idea of like, the weight of an object. Or you could say, it's 100 degrees, and you kind of like have a relative idea of what it means. But with calorie, that's kind of weird. We see that on the back of food labels, but it is a measurement of heat. So a calorie is equal to the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. It's kind of a neat thing to learn, right? So we also said that heat is measured in joules. So because heat is a form of energy, we do measure it in that sense as well. And then, so 1 calorie is roughly equal to 4.18 joules. And so when you see how many calories are in like a certain, food, it's kind of telling you like this much energy is going to be needed to burn off this food. So it's a really neat sort of way of measuring it, and it has these really broad implications. So you have a little visual there. You can always go back and look at it, but it doesn't really pertain too much to what we're doing. So how is heat related to thermal energy? So adding or removing heat from a substance will affect its temperature and its thermal energy. Heat is not the same as thermal energy, though, nor is it the same as temperature. So thermal energy and temperature are properties of a substance, to where heat is the energy involved with these property changes. So that'll be something that you want to keep in mind when you're going through the CK12 adaptive practice work, is that the thermal energy and the temperature, those are properties of a substance, while the heat is the energy involved with the properties changing. So even though two materials might have the same temperature, their thermal energies are going to be different, like we saw with the examples of one of them being larger than the other. So thermal energy depends on how many particles are present in the object. So energy as heat will be transferred from the warmer body to the colder body until both are at the same temperature. So if you had that ice cube sitting in your hand and it starts to melt because the heat from your hand is going into the ice cube and melting it and turning it into water, eventually, if you just held it there, that water would become the same temperature as your body. And that's when it's set to be in equilibrium. So how can heat affect the state of an object? Well, the state of a substance depends on the speed of the particles. So if we impart more heat, we're going to make those particles move and vibrate even more. and it'll change the state of the object. So adding energy in the form of heat to a substance can result in what's called a change of state. So water is the easiest example here. If we have, solid water, which would be ice, liquid water, and then we have, gaseous water, which would be like water vapor. Each of those are just water with different states of energy. And so when we say that's going to be a change of state, we are changing that state of matter. So if we have, that ice cube as a solid, once it melts and it's all water, now it has gone through what's called a change of state and is now in the liquid phase. If it keeps getting heated up and it becomes steam, that is once again a change of state, and it is changed. So removing energy in the form of heat can also result in a change of state. So notice we're not saying something's getting colder because you can't attain that coldness. All you can do is lose heat. Therefore, if you remove energy, you can change the state. So if I had, liquid water and I removed energy from it, then it would turn into ice. You can say like, oh, you're freezing it. Absolutely. But what you're doing when you're freezing it is you're removing energy from the water. And so you can add energy in the form of heat, or you can subtract energy in the form of heat. Notice we're not talking about anything getting cold. So here's a little graphic for you. So we can see here, if we just took water to be the perfect example, solid water is going to remain at a constant temperature until it melts. And so when it melts, that's when we get that change of state. And then once it's a liquid, it'll stay liquid for a long time until it gains enough energy to become a gas, in which case you would once again see a change of state. So we want to talk about the three different ways that heat is transferred. And the three main ways are conduction, convection, and radiation. And if you're with me next semester when we go to earth science, we're going to be focusing a lot on convectional heat because it plays into a lot of different earth systems. But so we have these three different forms that we're going to talk about. And so we're going to start with conduction. So with conduction, it's the transfer of energy as heat from one substance to another through direct contact. So there has to be a direct contact there in order for conduction to occur. If you put your hand onto, like a hot surface, the heat from that surface will conduct its way onto your hand and burn you. Same way if you're holding an ice cube. Via conduction, the heat from your hand goes into the ice cube and melts the ice. So as long as the two objects are in contact, the conduction will occur until those two objects reach the same temperature. So that's what, if you ever heard of the term a conductor, that's what we're talking about. So a conductor is a material that transfers heat very, very well. So metals are typically great conductors because they will move that heat around. So if you've ever been like heating up like a metal object, whatever it may be, you may feel like even if the flame's far away, you may feel your hand start to get hot because that metal is conducting the heat all the way through the length of that surface. Now, opposed to that is what we call insulators. So insulators are materials that are poor conductors of heat. So like wood, paper, some plastics, those are really good examples of insulators. Silicon is a great insulator. So most oven mitts, like heavy-duty oven mitts, are made of silicon because it won't transfer that heat. It won't conduct it into your hand. It absorbs it, and it does not transfer it. So if you look at these, so if you're wearing like a flannel shirt or a sweater or something, the question would be like, well, is that a conductor or an insulator? So all that flannel shirt is doing is holding in the heat, not allowing it to conduct its way out. So that would be an insulator. To an iron skillet and a copper pipe, we talked about before in the past slide, how metals are great conductors. And so those, if you heat them up, it spreads the heat over its surface. And so those are conductors, both the iron skillet and the copper pipe. The oven mitt, like I was talking about, even though this one isn't silicone, it looks like it's cloth or some sort of fabric. It would be the same way. It would insulate. It's going to protect your hand from the heat because it's not going to transfer it via conduction. So we also have convection. They don't talk about it too much in your CK12 unit, but it's important for us to know. So convection is just the transfer of energy as a heat by the movement of gases or liquids. So you have the graphic down here in the corner, which is good for us to look at because convection will occur when a colder, denser mass of gas or liquid is replaced by a warmer, less dense mass. And now the big thing there is we have to look at the masses. The relative masses here are what causes us to really work. And so if you look at the diagram here, the water that is at the bottom of that pot, which is very close to the flame, it is going to be a conduction because it's so close. It's going to take in that heat from the flame. And then what it's going to do is it's going to become less dense because those particles are vibrating so much, it lowers the density. Well, since it's a lower density, it's going to rise up, just like warm air rising, in a house. So when water is boiled, the water moves in roughly circular patterns because of this convection cycle. And the motion is due to density differences. The relative density between the hot and the cold are what cause this motion to continue. And so this is what we call a convection current. And this has implications not only for like the water that we see here, but for the water in the oceans, water in lakes and ponds. It has to do with the molten material within the earth. It has to do with weather systems. Hurricanes are a major factor here when it comes to convection. And so we discuss all of that in earth science, which is really fun. But in terms of convection, this is how heat is transferred by that method. So like I was saying, we're going to see this a lot. So the winds that you feel are typically because of convection, hot air rising in a house or on a land surface or molten material within the earth, all sort of rely on these convection cycles. And the reason all of these work is because of the differences in density. And so lastly, we have radiation. We hear that term radiation and we think, bad. We think Incredible Hulk type stuff. But with radiation, you may have heard someone say like, oh, they have a smile that just radiates. Same concept here. So radiation is a transfer of energy by electromagnetic waves. They're back. We don't really get away from those electromagnetic waves. And so an example of those waves, like we've been talking about, visible light, microwaves, infrared, ultraviolet, those are all examples of electromagnetic waves. And so when radiation is emitted from one object and then absorbed by another, the result is we have a transfer of heat once again. And so radiation can travel through empty space. It doesn't need a medium to travel. And if you don't believe me, step outside in the middle of the day on a sunny day. You're going to feel your skin getting warmer, being warmed up by the sun. And so all that is ultraviolet waves, part of our EM spectrum, traveling through space. So it goes from, the surface of the sun, travels for 8 minutes to hit your skin, and it warms you up. So something that is 93 million miles away is warming up your skin via radiation. That's pretty cool. But it's another way that we can transfer energy. So if you've ever been around a really hot object, you don't have to touch it to know it's hot. If you just put your hand around it, you can feel the heat coming off of it. That is heat that is radiating off of that hot body. Therefore, we have thermal energy and heat transfer by radiation. So practical use of radiation, keeping us alive is really, really nice from the sun, which is awesome. You can have these solar cookers, which sort of focus in the sun's rays to a certain spot to cook, food. So solar cookers use radiation. And then in parts of the world that are far from electricity and clean water, solar cookers are a really cheap and portable way to sterilize water for drinking or to cook food. And you can make these with literally tinfoil. All you need to do is a little bit of math to figure out where the focus point would be, and then you can create a solar cooker on your own. An example I used to have my students do when I was a math tutor is we would make little parabolic solar cookers, and then we would cook hot dogs on them right in the middle of the day. It was awesome. So many people like to use those solar cookers because they do not require any fuel and they don't release any harmful emissions. It's really a pure and clean way to cook food or sterilize water just by radiation. And so it's a very important method of transferring heat. So you have this example here. If you want to come back to it, you can always do that. I'm not going to spend too much time going over it because this is a longer slide. but just know that these are the different examples of heat transfer. So if we have heat is the transfer of thermal energy, and we can transfer it three different ways. We would have convection, we would have conduction, and we would have radiation. So that's one of the overviews of what we just went over. All right, so with heat, we said it was the flow of thermal energy from one object to another. And so here, once again, is our discussion board question. So you have that hot cup of coffee in your palm, and the heat by conduction is going from that mug. The heat is being transferred into your palm. Now, opposite with the ice cube, since it is a colder body, the ice cube is sitting there on your palm, and your palm is radiating. Not radiating, is conducting heat into the ice cube, raising its temperature and making it go through a state of change. It changes from a solid to a liquid. And so the thing to take away from that is that heat always flows from a warmer to a cooler object. It cannot reverse and go the other way from a colder to a warmer. It violates all types of thermodynamic laws, and the universe as we know it would cease to exist. So don't even try it. All right. So there's our electromagnetic spectrum. Once again, we're never going to get away from this. It is one of the things that makes the universe work as it does. All right. So let's look at some of the questions that you're going to see on CK12. So I went through the adaptive practice. Now, it doesn't allow me to see all of the questions there. And so I went through, and I just selected a few from each section. So these are some that you might see, and we're going to go over why they are the answers that they are. So the first one there says that thermal energy of matter depends on its, and then it gives you all those options. So the correct one there is going to be all of the above, because it's really important to know that mass is part of thermal energy, the temperature, and the number of particles. And if you go back to this slideshow, you're going to see that we talked about each one of those: the mass, the temperature, and the number of particles. That's what the thermal energy depends on. Then moving over to the right there, so thermal energy and temperature both relate to the amount of what energy in moving particles of matter. So the hint there is the moving particles of matter. If they are moving, it has to be kinetic energy. We talked about potential energy, which is the energy that is stored up, but is not the energy of motion. So down here, I purposely put this one is in as an error or as an incorrect answer, just because I can totally see people putting this and being confused on why they got it wrong. So it says the average kinetic energy of particles of matter is called what? And so I can understand someone saying heat. Well, if they're vibrating more, they're going to have more heat to them. But what we'd actually want to put in there is that the average kinetic energy of particles of matter is called temperature. So that temperature is that average energy of the particles, as opposed to the total amount, which would be the thermal energy. So this next one says, which one has more thermal energy? A cup of hot coffee, a bathtub full of warm water, a pot of soup boiling on the stove, or an ice cube in a glass of lemonade? So we have to take into account all the stuff from this first question here: mass, temperature, and number of particles. So hot cup of coffee, yeah, that's going to have a lot of thermal energy, but the amount of particles in it is nothing compared to a bathtub full of warm water. So automatically, A goes out because B is much larger and it is warm. So you'd have much more thermal energy. Now it says a pot of boiling soup on the stove. Now it's boiling, so it must be way hotter than the bath, therefore must have much more thermal, not eternal energy. Eternal energy is, something that the gods have. But anyway, that's for like a mythology class or something. But so that pot of soup boiling on the stove has a ton of thermal energy, but once again, it is not very large. Even though it is larger than the cup of coffee or the ice cube in the glass of lemonade, it is not as large as that bathtub full of warm water. Therefore, that bathtub full of warm water is going to have the most thermal energy out of all those. So now that second section that you have, you're going to have to do a little bit of math in there, and it explains how to do it in that section, but you're going to have to convert between Fahrenheit and Celsius. Now, I know that nobody's just going to go to Google and put in convert 73.9 Fahrenheit into Celsius. I know no one's going to do that. Right. Why not? That's what I did. Make it easy on yourself. I'm not going to be there checking this stuff. Make it easy on yourself. So there's a whole formula to this, and it's that the degrees Celsius is going to be equal to 5/9 times the temperature in Fahrenheit minus 32. And then we just got to plug in our known and solve for the variable of the unknown, and that tells us what we need to be. Or your buddy Google can do it for you. But no, and so I say that, but I kind of joke. If you want to use the formula, please feel free. There is stuff like that in the CK12 that explains it. And then also, as you're working through, you can find a lot of stuff that will show you how to convert from one to the other. But essentially, what you're going to be doing, if you knew the temperature in Fahrenheit, you'd take the 73.9 and you'd subtract 32 from it, and then you'd multiply it by 5/9. And what that would give you here would be 23.3 degrees Celsius. And so you can see the temperature differences between these. So you might think, ooh, 23 degrees, that's cold. But that's Celsius. In terms of Fahrenheit, that's 74. That's a lovely day. So now they talk about another temperature scale, which is Kelvin. And so the boiling point of methanol is 64.5 degrees Celsius. What is the boiling point in Kelvin? So once again, you can Google how to do this. You can look at how it's done on CK12. But essentially, all we have to do is we have to take the 64.5 and the Kelvin temperature scale just means we have to add 272.15 to it. So if we do that, 64.5 plus that temperature in Kelvin would give us 337.65. Now, they always say round to the nearest tenth, so we only want to take the first digit after the what period? I don't know. What do we call that? Decimal point. There we go. That's the name for it. All right. Yeah. So 337.7 tenths is the first digit right after the decimal point. And so that would be our answer. Whew, man, that was bad. Period? What am I thinking? Come on. It's not a sentence. But anyway, so a student experimentally measured the boiling point of benzene and found it to be 177 degrees Fahrenheit. That sounds like a great experiment for a student. What is the boiling point of benzene in Celsius? Okay, so once again, so the formula is right down here. And so we would take our temperature in Fahrenheit. We are going to subtract 32 and then multiply by 5/9. And that gives us, 80.5556. Once again, we just want to take the first digit after the decimal point. And so we're going to have 80.6 would be your answer that you'd pop in there. But it's just all based off of that formula. All right, so then another one, which could be, I picked this one because what they say here is pretty confusing. So they say this thermometer here shows the temperature in Celsius. So it's right at 24 degrees Celsius. And it says, what is the reading in Fahrenheit? So we just use that same formula, except now you're plugging in what you know for Celsius, and you're just sort of reverse engineering your answer to get the answer in Fahrenheit. But the thing here is they say use 3 significant figures. Now, significant figures is something that if we were being sticklers on everything we were doing, we would want to talk about significant figures. But essentially, all it's saying here is use 3 digits or, 3 sort of placeholder areas for numbers. So even if you did this math out and you got like 74.22 or 75.22, they wouldn't want that extra 2. Just give them the 75.2, and that's all they're going to ask for. So that would be your answer there. And then also this says, which of the following is the most appropriate word for the fill in the blank? Heat, thermal, or kinetic? So after hot cocoa is poured into a cold mug, blank energy from the hot cocoa is transferred to the cold mug. So if we have heat transfer, that's just going to be thermal energy that is being transferred from the hot cocoa to the mug. All right, so a couple more. So thermal energy is the blank energy of particles in an object. And so thermal energy is the total energy of particles in an object. Now, this one could be a little bit tricky because another thing that they're going to talk about there is the kinetic energy of particles in an object. So just make sure you're keeping those straight. And if it gives you an incorrect assessment or an incorrect grade on that, let me know. I have no problem changing that over because I totally get why you may put something else in there. They don't really specify too well with some of these questions. And then you have a couple that are select all that apply. So if it says like temperature is, you have to read each one and say, does this apply to temperature or does it not? So is temperature equal to heat? No, not really. Temperature is just measuring the amount of thermal energy. And so that second answer, B, temperature is a measurement of thermal energy. Yeah, it is. And so we'd want to click that one. And then next one says temperature is able to change based on surrounding energy conditions. Oh yeah, absolutely, 100%. So you'd want to pick that one as well, because if the energy conditions, if energy is imparted, the temperature will raise up. If you take energy away, it will plummet. And then it says temperature is a constant value. No, if it was a constant value, no weather person would have a job, and it would just be chaos. You wouldn't even need the weather apps that are all fun. It would just be like, it's constant. What are you looking at the app for? I'm sorry, that was just terrible, all the way around terrible. But anyway, so a couple more. So there's a net flow of thermal energy transferred between two substances until. So when does that energy transfer stop? Only when they both reach the same temperature. That's when it stops. I just know that one was worded a little weird. So thermal energy is transferred between substances only when they have different. So it's not masses, it's not volume, because you can have something with small volume, like say if you had like a big block of ice and you heated up a marble, like a little glass marble, to a couple hundred degrees, and you dropped it on that ice. The masses are going to be different, the volumes are going to be different, but that little glowing hot marble is going to transfer a lot of heat over to that block of ice and change the state pretty quick. And then so temperatures on there. So thermal energy is transferred between substances only when they have different temperatures. So if the temperature is different, then you can have heat flow and energy transfer. And then the last one says two of the above. That's just a weak attempt at throwing in like a weird answer in there. They didn't even give us the decency of putting all of the above in there. They just put that out there, and I don't know. That's lazy quiz writing right there. Lazy. They were in a hurry to do something, and they were just trying to get out the door. It was like 4:59 on a Friday, and this was the last question they were doing, and they shortchanged you on it. And so as soon as I'm done with this, I'm gonna write an email to those people at CK12 and let them know to stop being so lazy and insulting you all with questions and answers like this. All right? I'm not gonna do that. Not at all. I'll tell you I'll do it, and honestly, how many people are watching up to this point now too? I'm probably just talking to myself here. So let me just go on about this cool show I'm watching called Alone, right? I'm not going to tell you about it. Check it out. It's on Hulu. It's really cool. But so that is our lecture for the week. I know it's a long one. I'm sorry, but I wanted to include these questions on there to help you through some of them. I look forward to seeing you tomorrow in the Zoom, and you'll be watching this after that. So I don't know how the timing works out, but hope you enjoyed the lecture. See you soon. Enjoy your day.